Hello everyone, welcome to the lecture 3 of this 5th module where we are discussing humidity and chemical sensors. In this part, we have discussed few transduction techniques to detect humidity, okay, and in the previous class we discussed that we will focus on capacitive and resistive humidity sensor in the next class. So today we are going to discuss mostly on capacitive and resistive humidity sensors, okay. As I have mentioned earlier also that 75% humidity sensor that exist in the market are based on capacitive principle. Therefore, studying this kind of sensor is of utmost importance in this course. So, several times I have mentioned that capacitive transduction technique usually can be based on several things, like if you talk about a parallel plate capacitor, okay, if I talk about a parallel plate capacitor, I can have a transducer based on changing this D if by some mechanism, if this separation of this plate is changing, okay, or if the effective area of these plates are changing, or the dielectric material which is there in between these two plates is changing its property, okay. So, the dielectric property of this material, if it is changing with respect to something, okay, I can use this simple capacitor or this parallel plate capacitor to detect that non-electrical stimuli, okay. So, humidity is measured by detecting moisture induced change in the dielectric constant of a hygroscopy layer which is sandwiched between two metallic plates, okay. Usually to increase the low level current, which is because of the dielectric property of these materials, usually you will find that interdigitated electrodes are fabricated. I have several times mentioned that these interdigitated electrodes are fabricated by lithography techniques, okay. So in this structure, in this device structure, usually this metallic layer is of thickness say 5 micrometer to say 100 micrometer for bigger devices, okay, and these fingers are also of similar size, say 5 micrometer to 100 micrometer. The gap between two plates, two fingers, which decides the sensitivity minorly, this is also in this same range, 5 micrometer to 100 micrometer, okay. I mean, these numbers are not to be precise. It can be say 1 micrometer device, it can be say 250 micron device, okay, depending on your lithography tool that you are using, and then you have a bonding pad because this is a two terminal device, okay. In between you have this dielectric layer, and usually the substrates are it can be a simple silicon substrate or SiSi2 substrate, or if you are making these devices on a flexible substrate, you can have PET or PDMS kind of structures, okay. So an air filled capacitor may serve as a relative humidity sensor as well, okay. So the dielectric constant of a moistured air is different than the dry air, okay. So using a simple air filled property of a parallel plate capacitor, I can make a relative humidity sensor or RH sensor, okay. This is majorly because moisture in the atmosphere change the air's electrical permittivity, okay, and this change occurs according to the following equation. So this is an empirical equation which governs the relative humidity air's moisture, okay. So this kappa is the dielectric constant of a moistured air, and this is typically equal to 1 plus 211 by T into P plus 48 PS by T into H total multiplied by 10 to the power minus 6, where T is the absolute temperature in Kelvin, P is the pressure of the moist air in millimeter mercury, PS is the pressure of the saturated water vapor at temperature T, again in the unit of millimeter Hg, H is the relative humidity in percent, and kappa is the dielectric constant of the moisture, okay. So this empirical equation governs the dielectric constant of a moist air. So using this equation, in fact, you can calculate the relative humidity percent. Okay. So if you see this equation, the capacitance is actually proportional to the relative humidity. Okay. So now instead of air, if the space between the capacitor plate is filled with some isolator, so now you have some specific dielectric material which is also having some, say, hydrophilic properties is now replaced. So this is replacing the air which was initially placed. Okay. So the dielectric constant of that isolator changes significantly upon being subjected to humidity, particularly for the material which is having little hydrophilic property. But please note that if the dielectric material is very high hydrophilic, is possessing a very high hydrophilic property, what will happen is this dielectric material will absorb water. Okay, this will absorb water and it will start to swell. So this is, say, the two parallel plates. Okay, so this is parallel plate 1, this is parallel plate 2, this is the dielectric material. Okay, this is the dielectric material. Now what is happening is it is subjected to moisture. Say it was initially subjected to 25% RH. Okay, now so that time it was properly working. Okay, now I have increased this humidity to say 90% RH. Okay, in such a high humid condition, if this material is possessing very high hydrophilic property, what will happen is it will start absorbing some water molecule from this. Okay, because of this, what will happen is it will start to swell. Okay, and this is the majorly problem associated with polymeric films which are used as dielectric material. Okay, so when it starts swelling, what will happen is this D is also changing. So it will be very difficult to characterize that the effect is coming because of this changing D or it is coming because of the change in the dielectric property of the material. Okay, so the capacitive sensor may be formed by a hygroscopic polymer film and the metallized electrode as deposit on the opposite side of this film. Okay, so the capacitance of a polymeric capacitive sensor is approximately proportional to the relative humidity, as we have discussed. This CH is equal to C naught into 1 plus alpha H. Okay, where this is your relative humidity and C is the capacitance when there was no humidity. Okay, alpha is a constant. Okay, so usually graphene oxide has been reported to possess very high humidity properties, humidity sensing properties, but then there are some metal oxides also which have shown capacitive humidity sensing properties, like CDS zinc oxide. Zinc oxide itself is a very good sensing material for a capacitive devices. Okay, then carbon nanotube and some polymer films, they also possess this capacitive sensing property, and there are several dyes which has been reported to possess some capacitive humidity properties. Okay, however, these capacitive sensors also possess some disadvantages. The advantages are the low cost in fabricating this, and the interface circuit is also not very difficult. However, there are certain disadvantages associated with this capacitive humidity sensor. First is inherently this possesses high hysteresis. Why? Because as I have mentioned that you have these polymeric films. Okay, they have this tendency of absorbing water molecule. Okay, so if you remember the definition of hysteresis, okay, if I plot a static curve, okay, say between say capacitor or say capacitance versus RH percent. Okay, say at for this film X. Okay, say at I am taking data at 10, 30, 60, 90. Okay, say at 10, so these capacitances are some microfarad, say 6 microfarad. Okay, this is 20 microfarad, this is 30 microfarad, this is 45 microfarad. Okay, so what is happening is, say at initially, say if I have increased this RH for this device from 10% relative humidity to 90%, say initially it was 6, then for 30% RH it went to 20, for 60 it is around 25, and for 90 it is around 35. Okay, this is my response curve on a static plot. Okay, now for hysteresis calculation, I should come back from 90 to 10. Okay, what happened that when you subject your device to this high humidity condition, and not only high humidity condition but continuous humidity, if you subject this device continuously to humidity, what happened that when you increase from 10 to 30, at 10 it was working perfectly fine, but at 30 what will happen is this polymeric film has tendency to absorb some moisture. Okay, so if it starts absorbing some moisture, okay, say if it absorb say 100 water molecules, okay, because of that what will happen is its capacitance changes permanently or at least quasi permanently. Okay, so if you will try to measure at 30 RH, okay, 30 RH percent, what will happen is this data will, along with the measurement data, what you also have is this quasi permanent change in the capacitance. All right. Now you consider the condition when you are increasing this humidity from 10% to 90%. Okay. Now at 90% it has tendency, because it is seeing more and more water molecule, it has a tendency to absorb more and more water molecules. Okay. So in that case what will happen is this will absorb very high quantity of water molecules. Okay, and that will shift this capacitance to somewhere at high position. Okay, so when you come back to 10, because if you remember how you calculated the hysteresis, what you did is you went on increasing the concentration of analyte, and then you came back to the minimum concentration level. Okay, so here you have increased the concentration from 10 RH percent to 90 RH percent, and then you come back from 90% RH to 10% RH. In that sense, what will happen is this will possess naturally a high hysteresis as compared to the other kind of devices. Okay, so that's why people have started exploring other inorganic materials also apart from this polymeric films to measure humidity or say RH percent. Okay, then second disadvantage of this capacitive humidity sensor is slow response time. Okay, since your device is working on a principle where this dielectric property is changing, so it will try to settle first in presence of humidity, and then only you will find that dielectric property is changing. Okay, so these changes are very minute and the response is very slow. Okay, then this was the history of this capacitor, but what you are trying to measure is change in the capacitor, delta C. Okay, so the output signal is relatively very low as compared to other sensors where you have change in terms of say current or something else. Okay, and also if you see, you are basically discussing the change in the charge as compared to other electrical parameter, current or voltage. Okay, then these devices are very temperature dependent. Okay, so if you elevate the temperature, these things will start behaving differently, because say 90% RH at room temperature, when you are subjecting it, it will have different property to absorb water molecule as compared to you are subjecting it to 90% RH say at 50 degrees Celsius. Okay, the adsorption and desorption phenomena at the surface of this material will be entirely different as compared to that of room temperature. Okay, so these are some disadvantages of capacitive humidity sensor, and although the resistive humidity sensors are not as accurate as capacitive sensors, capacitive humidity sensors are, but they have gained a lot of attention in recent past. Okay, so the transduction mechanism of a resistive humidity sensor involves basically change in resistance or change in conductance. Okay, this change in resistance or change in conductance is coming because of the adsorption of the water molecule at the surface of this film. Okay, the fundamental structure of these sensors is very similar to the capacitive humidity sensor, where you make this interdigitated electrodes, except there you were using some dielectric material, but here you are using some semiconducting material, and there you were measuring the change in capacitance, here you are measuring the change in resistance or say conductance. Okay, so here the dielectric layer are substituted with a material whose conductivity or conductance actually varies with humidity. So this is a typical resistive humidity sensor. You can see that mostly these devices are fabricated on ceramic substrate to make it cost effective, as well as to repel the water molecule and to ensure that the results that you are obtaining is coming from the device. Okay, so this is the COM kind of structure that you are already acquainted with, and I am calling it regularly interdigitated electrodes, or IDE, or sometime IDT. Okay, and this is the base electrode and the probing points where you actually probe your device. Okay, usually this comes with humidity sensing film, and sometimes you also use some protective film to protect your humidity sensing films. Okay, the electrodes are usually silver, platinum, or gold kind of electrodes. Usually you avoid using aluminum and other materials. Okay, so this is the principle of resistive humidity sensor is also very similar to capacitive sensors, except here the change that you measure is particularly based on change in resistance or capacitances. Okay, let us take an example of one material. Okay, usually new kind of materials are emerging to for developing this kind of devices. Say tungsten sulfide, this is a very well known material which is used as a sensing layer. I have mentioned that in the resistive humidity sensor, what you are using it, you are using a material which can change its conductance or resistance in presence of humidity, as compared to capacitive humidity sensor, where the dielectric property of the sensing layer was changing. Okay, so such a material is a tungsten sulfide. It changes its property when it comes in contact with humidity. Okay, so WS2, what happen is, the structure of WS2 is very simple. Okay, so you have a tungsten atom and you have two sulfur atom. Okay, similarly you can make a say side view of this structure, something like this. This is I am calling tungsten, this is I am calling a sulfur. Okay, now when water molecules come in contact with this, what happen is, it tries to make say van der Waals force, or say sometime hydrogen bond between this tungsten and H2O, or even with sulfur. Okay, so when this all these points are occupied by water molecule, then there is another layer of moisture that is attached to this H2O by some weak physical forces. Okay, then third layer, which I am calling the bulk layer, okay, and fourth layer, subsequently fifth layer of water molecules go on forming. Okay, similar mechanism has been proposed for several metal oxides, and this is a very well known mechanism in humidity sensing. It is known as Groth's mechanism. Okay, so when you have this kind of structure, okay, the last layers, particularly after the third layer, this water molecules forms a kind of bulk layer. Okay, and you have some H positive ions, which can hop among this network. Okay, therefore apart from the electron conductivity, this resistive humidity sensors are sometimes also based on proton conductivity, because if you see, this H positive is nothing but a single proton. Okay, so because of this hopping of this H positive in this bulk layer, sometimes you find the change in conductance or change in resistance. Okay, so that's why most of these devices, particularly metal oxides and some other organic molecules also, okay, they show this Groth's mechanism where the conductivity is not based on, or the change in conductance is not based on electron, but it is based on hopping of proton. Okay, so this is all about humidity sensor. I hope that you have learned what is humidity and what kind of sensors you see for this humidity detection. Okay. Then since we are discussing humidity and chemical sensors, okay, our next job is to understand a chemical sensor. Okay, here you can see that these chemical sensors are mostly inspired by nature only. If you see this boy, okay, he's showing that chemical sensors can be based on this smell and taste, which is of course very natural. Okay, but then there are physical sensors also, again, which is derived from nature only, be it touch, be it hearing, be it sight, or be it simple pattern recognition, okay, of all these things. Okay, so chemical sensor, whenever we say, we mostly talk about smell and taste. Okay, at least in this course we will be discussing smell, which is detection of some gases which can be toxic, which can be non-toxic depending on, but it can be, you know, explosive in nature. Okay, so we'll see some of the gas sensors under this heading of chemical sensor. Okay, so as the natural process of detecting something is like we have various sensory receptor in the brain, in our body. Say for example, my skin is a sensory receptor. So if someone pinch it, I have a sensory which will detect it, and the information will pass to the brain, where the information is processed that okay, this particular person has pinched you, or something else has bitten you, or something else. Okay, the process of sensing or say process of gas sensing is also very similar to what we have seen for this natural process, except that we have a receptor and a transducer. Okay, we have a transducer, right? And of course then I have a whole electrical circuit. Okay, so I have a sensory receptor which is at forefront, where my gas molecule, say gas X, Y or Z, it will interact, and this information will be transferred as an electrical signal by this transducer, and this electronic circuit will convert this signal, amplify it, pre-process it, whatever it can do. Okay, and then it will be sent to a computer or say microcontroller, where the information is processed. Okay, so the basic construction of a gas sensor is, you have a sensory element which is called receptor, then you have a transducer, you have an analog circuit where the amplification and pre-processing happen, and it is sent to a microcontroller where the information is processed. Okay, based on the transduction technique, you can have a number of gas sensors. You can have a simple chemi-resistive devices where the change in the resistance of a thin film is measured with respect to some gas molecule. I have been giving this example regularly. Say consider this is a thin film of some material. All right. Now some gas molecule, okay, when interact with this surface, okay, can either donate electron or take electron from this. Okay, based on this charge transfer, okay, I can have change in resistance of this film, or I can say change in conductance of this film. Okay, since this is happening because of some chemical phenomena, okay, I call it a resistive device. So this is a resistor which is changing its resistance with respect to some chemical, and I am calling it a resistive device. Okay. Say we have also seen piezoelectric devices where this change is because of change in the mass. Okay. I can also have capacitive devices where change in capacitance is happening because of the interaction of the gas molecule with the sensing film. The sensing film can be in the form of a dielectric material. Okay. Then I can have specialized devices like field effect transistors, okay, where you can find a change in the work function or change in the channel current, okay, because of this kind of interaction, be it at drain or be it at some other place. Okay. So similarly, you have electrochemical devices where change in electromotive force or EMF happens, or change in electrical current happen because of the interaction of some material with gases. Okay. Optical sensors can be based on a number of phenomena. Okay. So it gives you highest order of control. Okay. So you can have reflection, absorption, interferometry, fluorescence, refractive index change, or even optical path length. Okay. And all these phenomena can be used for a optical sensing purpose. Okay. So we may not be able to study all these gas sensing transduction principles in this course, okay, because it may require special skills to discuss this, but then what I can do is I will discuss some of them in the next lecture, or including today's lecture. Okay. But why these gas sensors are so important that we are studying in this course? Okay. So there are several growth drivers which has propelled the research in this domain, and even industry has also started looking these devices with a lot of promise. Okay. So increasing government initiatives and regulations regarding worker safety is of utmost importance. Okay. Say if you are sitting in a room or in a classroom, okay, you have to see that the wall around you is painted. Okay. These walls are painted using some polymer coating. Okay. And if sunlight is falling on it, or even if nothing is happening, then also these walls are emitting some volatile organic compound. I will be using a short abbreviation for it, VOCs. Okay. So this volatile organic compounds sometimes can be very hazardous for you. Okay, if you are subjecting to this gas continuously for over 8 to 10 hours. Okay. So government imposes some rule and regulation that if the employees are working in this industry, or if he is sitting in this office, okay, what VOCs all he can be, he can be subjected to, and how it can be minimizes, what can be the health impact of these gases on the worker safety. Okay, all those things has gained importance in recent time, particularly with the rise in the smart cities and smart homes. Okay. So then rising adoption of gas sensor in automotive HVAC systems and emission control systems is another parameter which is driving this growth. Okay. Then increasing utilization of gas sensors in the oil and gas industry for process optimization is the another growth parameter. So all this, not only oil and gas industry, but if you talk about pharma industry, agriculture industry, food industry, everywhere this gas sensors is playing important role. Okay. Then another factor that is helping this area to grow is the rising demand for wireless gas sensors from customer electronic applications. Okay. Then air quality monitoring in smart cities is nowadays is very common, particularly with this wireless sensor network, and it has increased demand for this gas sensor. Then integration of IoT and cloud computing technologies is another growth driving parameter for the rise of this gas sensor. Okay. And then finally, the industry automation has been acquainted with these gas sensors, and now it has been integral part of this automation systems. Okay. but there are several pitfall and challenges in developing these gas sensors at industrial scale, particularly the design complexity associated with these sensors and the shorter lifespan of the sensors. Particularly if you are talking about polymeric devices, the lifespan of those devices, be its shelf life or be its operational life, are much smaller. Okay, then effect of humidity is the biggest issue in developing these gas sensors. All these polymer films, they are very vulnerable, and they changes its property when it is subjected to humid condition. Okay, particularly high humid conditions. Okay, this will also have impact in changing the baseline. Okay, so we call it a baseline drift, and usually these are considered as ambient condition, particularly the change in temperature and change in pressure or change in humidity around the sensor. Okay, so it causes the baseline drift of the device. Okay, then finally, the biggest challenge in developing these sensors are its selectivity. Okay, as I have mentioned that particularly for chemi-resistive devices, as I have mentioned that the change in resistance is basically because of transfer of charges from the gas to the material. Okay, usually these materials are n-type semiconductor or p-type semiconductor. Okay, and these gases are oxidizing gases or reducing gases. Say for example, if it is a reducing gas and the sensing film is a p-type material. Okay, so I have a sensing film which is a p-type semiconductor. Okay, and I have oxidizing gas or say reducing gas which is purging on it. Okay, because of this reducing gas, okay, I am writing it, since it is a reducing gas, when this device is subjected to this gas, since it was a say p-type, what will happen is it will start, or say it is a n-type material, what will happen is the initial conductivity of this film was because of flow of electron. Okay, now this is a reducing gas. What will happen is it will again donate electron to this film. Okay, and initially say there were 4 electrons in this film. Now this has donated another electron, so now I have total 5 electrons in this n-type film. Because of this, the conductance of this film will increase or resistance of the film is decreasing, and you can think of just opposite in case of p-type material. All right. However, the catch is this, that all these gases, I mean, there can be number of reducing gases, say R1, R2, R3, R4. Okay, and all this R1, R2, R3 and R4 have capability of changing this conductance. Okay, or everyone can interact here. Okay, of course we can classify them based on their absorption energy or by other phenomena, but initially if you see, all this can donate electron, and if you quantify this, if say if it is the change in resistance, say this was the initial resistance, this is the final resistance in presence of gas, I am calling it Rg. So initially the resistance was R0. In presence, when I am subjecting it to some gas, okay, the resistance is changing to Rg. Okay, now for all this reducing gas R1, R2, R3 and R4, these changes can be, there can be changes for all R1, R2, R3 and R4. All right. So as you can see that there are changes because of all these gases. Sometimes it is very difficult to segregate that, okay, this sensing is because of gas R1 or because of R2 or because of R3, and that is the classified under the issue of selectivity. Okay, so this is one of the utmost challenge for a gas sensor. Okay, application of gas sensor is not limited to only pollution monitoring. But it has went to monitoring the smart farms, be it greenhouse or something else gases. Okay, be it say gases participating in the nitrogen cycle of the earth or something else. Okay, in smart homes you need several type of gas sensor, be it LPG monitoring or be it VOC monitoring in the room. Okay, similarly in industry n number of gas sensors are required. Okay, and in smart city of course you require variety of sensors, because you never know that which industry is going to emit which gas. So you need actually a plethora of sensors install if you want to make a smart city. Okay, then there is one more important application of this gas sensor, which is in the healthcare. Okay, so in healthcare, how it is important apart from this pharma industry is in the as a breath analyzer. Okay, so if for example, if you consider that usually we think that we take oxygen and we exhale carbon dioxide, but along with carbon dioxide we exhale more than 4,000 odd gases. Okay, some of the gases can act as a biomarker for the underlying disease conditions. Okay, one example is for ammonia. So usually in healthy individual, this ammonia concentration in the exhaled breath is around 150 ppb to 500 ppb, and for some of the diseases it increases this concentration from 500 ppb to even 1.5 ppm. Okay, so that is huge. Okay, if you can calculate or if you can detect this change from say 500 ppb to 1.5 ppm, you can easily tell, at least you can screen that if he is a healthy person or if he is an unhealthy person. Okay, then this is just one example for ammonia, particularly for renal problems and liver disorders, but people has reported a number of gas sensors which can be used to monitor a number of biomarkers for different diseases. I have listed out some of the diseases and their biomarkers. Okay, in the next class we'll discuss in detail about gas sensors. We will also try to cover some of the transduction techniques for this gas sensors. Okay, thank you.